This video is for Chapter 4, Section 6. We will be looking at the hypotenuse leg theorem as the final triangle congruence theorem. Prior to this lesson, we have studied 4 different ways that we can prove triangles congruent. We have the side-side-side, side-angle-side, and angle-side-angle postulates, and we have the angle-angle-side congruence theorem. These are the 4 different ways that we can prove triangles congruent. One of the ways that we cannot prove triangles congruent is to use side-side angle or angle side-side. We've discussed this a little in class, but we haven't really looked at why. ASS, not only is it bad for us to say, but it actually doesn't work. I'm going to go through and look at 2 different ways that we can help see why these don't work, and they're going to lead us to this final theorem, the hypotenuse leg theorem. We're going to start off with an isosceles triangle, and we're going to remind ourselves that if 2 sides of the triangle are congruent, then the angles opposite those sides are congruent. Now, I can take this isosceles triangle and draw a line from the vertex angle to any point on the base. From the vertex to any point on the base. So let's do this. Now, 2 triangles have been created. Don't look at the big triangle anymore. Look at the 2 smaller triangles created inside. This triangle, if I start here, has an angle connected to a congruent side connected to the double angle mark. And this piece right here is congruent to itself. Now, triangle number 2 has the exact same angle connected to the exact same side, connected to the exact same side. These 2 triangles have the angle side-side relationship. But very clearly, this triangle is not the same as this triangle. This triangle appears to be an obtuse triangle. This one appears to be acute. They have angle side-side relationship, but they are not congruent. If a triangle has side-side-side relationship, it is guaranteed to be congruent. Angle side-side, not guaranteed. Let's move the line. Do we have the same thing? Angle, side, and then a side. And this triangle has the exact same angle connected to the exact same side, connected to the exact same side. Again, 2 triangles, 1, 2, that have the same angle connected to the same side, connected to the same side. Not congruent. Well, is there a way that they will be congruent? What if we were to draw that line down the center of the isosceles triangle and we were to bisect the base? So we have to come straight down. Well, the only way to do this is to actually bisect the opposite side. Well, that cuts the triangle in half and effectively gives us side-side-side. So therefore, ASS is not something we would have to worry about. Also, if we remember from our previous unit that if this is the case, that we connect to the midpoint here, that would also cause these angles here to be congruent, and it would cause us to have right angles. And now we have all kinds of stuff here. We have bisected angle at top, we have angle side angle, we have side angle side, side angle side, side side side. No need for the angle side side relationship. But this one time was because we came straight down. Notice it formed right angles. Let's look at another example. Here I have a segment, an angle, and then a red segment. The black segment is intended to go on forever. Let's start with this angle and red, this side. What I'm going to do is I'm going to connect the red to somewhere on the black. So I'm going to start with an angle and extend the side red, and then we could swing a pendulum to see where we can hit the black. For example, I could draw this blue line right here, and I could have an angle red blue, but if I swing this pendulum over here, I could still go angle red blue. Now let's separate these 2 triangles. Here's one, angle, red, blue. This triangle goes angle, exact same red, exact same blue. Now this is an optical illusion, but the red in these two triangles is exactly the same. The blue is exactly the same. What's different is the black. So these triangles have angle, side, side, angle, side, side. Again, angle, side, side is just not working. Now, the only way that this would work is if this blue length had not come down at an angle, but rather come straight down. Now, if we swing the blue, it can only hit at one spot. So again, the angle side side is not working except when it happens to form a right angle. This leads to the hypotenuse-leg theorem. It tells us that if the hypotenuse and leg of right triangle are congruent to the hypotenuse and leg of another right triangle, then the triangles are congruent. So, as I look here and I say right angle, side and a side, right angle, corresponding side and side. This kind of looks like angle, side, side. And with the fact that all right angles are congruent, this really could be angle, side, side. This is the one time it works. So we can't call it angle, side, side because it doesn't always work. So we call this hypotenuse leg because in a right triangle, the largest side or across from the right angle is considered the hypotenuse. This side is considered the leg. So the key is we have to say they are right triangles, not congruent angles. In a proof, you must have two congruent side statements, hypotenuse to hypotenuse, leg to leg, and you must state that they are right angles. Then you have hypotenuse leg. This is the only time ASS works, is if it's actually hypotenuse, leg, right triangle. What does it look like in a proof? Okay, given AC is congruent to FD, marked. BC is congruent to ED, marked. And B and E are right angles. So if I have all this as given, the only thing I need to say is that they are right triangles, because hypotenuse leg is only true in right triangles. Given, there's our hypotenuse, there's our leg. Well, that gives us right angles, but that's not enough. I could either say that these angles are congruent, and this would become ASS, or I could say that these are right triangles and produce hypotenuse leg. So I'm going to say, come on, triangle ABC and triangle FED, notice the order is correct, A matches F, are right triangles. There is a difference here, not right angles, right triangles. By definition of a right triangle. The definition of a right triangle is a triangle with a right angle. A triangle with a right angle. This is the one key ingredient to using hypotenuse leg. You must have a hypotenuse, a leg, and you must say they are right triangles. Now the triangles are congruent by the HL theorem. Still three critical ingredients, but instead of three congruent parts, we have two congruent parts, hypotenuse, leg, and the third ingredient, which is right triangles. That's it for the hypotenuse leg theorem. This is chapter 4, section 6, and you can now begin this section's assignment.